Okay, and we're back. Oh, that's kind of tight. Um, just woke up. Let's go to work. So Friday. Um, this computer sometimes. Okay. Multiple fermosecond optic harmonics. Yeah, this one was way over my head. I don't know if I couldn't. There was nothing. I don't remember this. I think I came in like halfway. Um, and this one, uh, I kind of remember, um, but I did not really. Anyways, we get into our next session speakers. Ultrasonic properties of brain scalp. So I guess ultrasounds don't really know much about the scalp, but they know a lot about other parts of the skin. The scalp has, yeah, it has its own kind of like circulation. It has unique characteristics, the human scalp, and so mapping it with ultrasound is important. Cecile, I hope I pronounced that right. I'm just bad with names. She was very sweet. She was also very nice. We stood in line together for lunch. This I don't remember, or if it happened. I'm sorry. Sleeping Beauty. Wait. I don't remember if I watched this or not. If I actually got to read this. Thermal stabilization of biologics inside glass vials using light assist drying. This is pretty cool. Yeah, helping to get vaccinations that with cold storage they could just use light drying. It seems promising. They're working through their problems and they're doing good work on that. So that's really cool. Model wounds of a model organism. This was pretty cool. Yeah, they're trying to understand uh, the different patterns of damage. So they used a fly, and they're just trying to get a base layer, base understanding of normal cellular damage. Hopefully, that could be later on because we know that there's a limited amount of crossover between like other biologies and others, but there's still some, and that because there is some, it makes this worth testing. And yeah, they used a little laser. They caused a small little hole, and they watched it heal itself, which was pretty cool. Um, People brought up different mechanisms like puncturing versus a laser, and they said you could do more damage than intended with a puncture wound, but it is something to test. Caden talked about the mathematical models of it, how to model it, and so it was pretty cool. It's a very well spoken young man, very smart. And so yeah, he talked about just the different modelings that he used to help analyze the data. Quantifications of tissue healing. I don't know if I got this one all the way. Okay, that's awesome. Sorry, Maddie, I don't really remember this one, but that's an awesome experiment. Oh, this is cool. They're trying to see if they can uh, imitate bird imaging on like what would stand out to a bird, but they're still limited by what we can use and what we can interpret, but they do to make effort. I don't know. Yeah, this one was above my head. On protein in the blood that helps with hematosis. Okay. Hemostasis. Hematosis, stasis. I don't know. Sounds very interesting, very important. They're talking about like soluble shear and stuff. That's so much physics. I don't know if we got to this one or if it was just another one that was so over my head that it just kind of, oof, you know. So that is that first lecture. Student lunch. I got so twisted around. I thought this is where the mentoring thing was. I didn't realize the mentoring thing was just a discussion. I thought the mentoring lunch was just like a conversation. Like I thought you'd get to sit down at a table with like some mentors or something, but they just had two people go up and speak. And so yeah, it was more of a presentation than a mentorship. This all right. This is the final set of lectures, and this one's gonna be. It was super interesting. Hang on, let me go get some. Forgive me. Mr. Takauchi. I mean no disrespect. He didn't like me. Yeah, he did not like me. So, which is ironic, honestly, because we were talking about kind of the same things in this talk. He wants to point out that the way of Newton's laws are often taught in classrooms is quite misleading, if not outright incorrect. And my argument to him right away was that calories are the same thing. And he immediately started to dismiss me. The third law is a particular problematic as an expression of the action and reaction, since reaction in physics terms is not reaction, everyday English term, which is how we are describing chemistry, and which is the exact point I'm trying to make about calories as well. And it was just so annoying that he absolutely dismissed me. He would listen to my points and then come up with a hypothetical to prove me wrong. But those hypotheticals are fiction, just like calories in nutrition. Yeah, they're not appropriate measurements. I will clarify shortcomings of the traditional approach and propose an alternative method which I believe is much easier for a student to grasp. Yeah, and he talked about momentum over time and then combining everything together. And his argument kept coming back to me was like, you got to have something else for people to get onto. And I said, I know that. I'm just trying to ask if it's bad physics. And again, he just kept talking to me about it doesn't matter if it's good or bad physics. And I just would not answer the question. I thanked him at the end, and he gave me a head nod and not another comment. And, we were walking the same way. He was talking to another guy, but I just I found a different way around. Like, it was just very uninviting. Exploring subfield interest development. This was super cool, man. I want to find this study. I need to contact her more because I want to write a paper on this. I want to go through this. I want to break it down. It's really cool. And I think based on how they have this model generated right now, I think they're missing some key elements that actually make that model useful for what they want to use it for, which is like trying to figure out how to keep people interesting, by understanding how students decide their interests. We can provide valuable insights for guidance professionals. Yeah, I think they just need to reweight some of the classes, or at least experiment with the weights. Yeah, it's gonna be more like weight setting, like you do in artificial machine learning models, than it would be weights in that we construct ourselves, because it's just like in the machine learning model, the weights are constructed mathematically from patterns, and so they should be done the same way here. Yeah, really cool stuff. And then this is just another extension of that. They're trying to develop the tool that goes with this thing, that part they're meeting. And then again, Tatsu did the Applied Physics Society. He did go over, I'm going to point this out especially because I got a little annoyed. He did have extra time. Okay, because I thought everyone had 12 minutes, and so they should have announced that, because I think several other people were annoyed thinking that he just got special privileges to go over time, unless they looked at the actual time. Dr. Anders Gardesting, very, very cool guy. He is a nuclear physicist. I was able to convince. And he was just very encouraging. He said, "What you say makes sense," especially because he used to do Faraday's lectures as well, and so that was really cool. He's taught Faraday's lectures, and so the things I proposed make sense to him, and he proposed a few experiments and or study designs, I suppose, and so I'm going to be listening. I'll be developing some more stuff. I did this waterbending experiment as well on ether dynamics. Oh yeah, talking about ether. So I think ether is a very interesting. I understand its physics has disproven it currently. You would have to explain all of general and special relativity, as well as this ether dynamics force. Let's see if they say it in here. It's supposed to be an incompressible, yeah, here it is, incompressible fluid that surrounds everything, and it propagates through space, exerting a force on any encountered object moving in ether. So I have three major questions. One, if it's incompressible, how does anything move? If it's everywhere and you can't compress this liquid, isn't that a solid? And so he tried to explain it to me, Mr. Jun Wang, that it's like if you drag your hand through the sand and make a line, you're not compressing the sand. And I had to really hold the fact that you do compress the sand. Movement requires a sort of compression of the surroundings. That's an interesting philosophy to kind of walk down. And so eventually he admitted it would be a small compression. So there would be compression. So that's one part of it. And then if the ether is everywhere in space, it is the fluid space medium. It is everywhere. Where does it propagate to through space? And then it exerts a force on any encountered object moving in the ether. But so we're talking about like ether currents, like currents in space-time, essentially, like under the ocean. Because my question was like, where is ether moving into if it moves into space? Like, what space is it moving into that doesn't already have ether into it? And I don't know if I helped him out too much or not, but we eventually agreed that it could be like ocean currents and vortexes. I think I might have brought that up. I was like, are you saying like kind of vortexes, like a water bowl? Like, because if you have a rock in a bowl of water that's filled to the top with no air in it, the rock will still move, surrounded by ether. But there'll be the noticeable drag of the rock, and I don't know if we have noticed that drag in light. I think we haven't, by our measurements. It's just the natural curvature of space-time creates a drag, and so there's a redshift in planets. And so my argument from if you watch the video on SciShow, if you have an unmovable object that is going to meet an unstoppable force, even though that's physically not possible, they both just phase through each other, because by definition they would have to find molecular alignments or atomical alignments that would just phase through each other, because one's unstoppable and the other's unmovable. So if this ether is everywhere, isn't it just the three-dimensional comprehension of space-time? It's just ether. Like, it is the space medium of space-time, and so it's not any different from space-time. So there's no like different kind of fluid. It is the everything that we are surrounded by. Like, because what does space-time pull onto? What does energy and gravity pull on? It pulls on the fabric of space-time. So but that's in 3 dimensions. It's not just like a flat plane like it's often described. So when it's a flat plane, then we're talking about like space-time planes. But then when we extend that into 3 dimensional areas, can't that just be the ether? That's my thought on ether. That it's no different than space-time, and so we don't really need to worry about it. But that's why all the equations line up with space-time. This one, I think, let's see which one. This one. This is William Rush. This was pretty cool. I like this one. He's saying that the universe is constantly expanding because gravity, I think essentially his argument is like gravity is pulling things into like the earth and everything. And so how is this energy of gravity conserved throughout the universe? And so the argument is that you're not, everything at the same time is getting added by space. And so we are like, space-time is just constantly condensing itself into the matter, but because everything is condensing itself at proportional rates, the physics doesn't change, I think. But wouldn't physics change? Would physics change with this kind of definition? I don't know. It was interesting to think about, because it tries to answer the question. It's the first time I've seen this question even kind of proposed like this, like where does the energy, if everything has a gravitational force that's pulling everything into each other, where is that pulling energy going to? And so that's what Mr. Rush presented. He was cool. Mr. Tatsu had some very pointed questions, just kind of, I don't know, didn't seem that chill. Oh, this one, okay, so yeah, solar system is the mass energy center, the black hole is the space-time center, and I could not understand the connections he was making. I think a lot of people just kind of pushed him away as woo-woo, but I do understand this dark star concept. Let's see, did he also do the... No, that's someone else. Okay. He did the idea of the dark star and the light star, and the light star makes matter, like we know with nuclear fusion, and the dark star, I think he was trying to argue, makes time, and so, and he also argued that Jupiter is one of these, is actually like technically a dark star. I don't know, man. I'm trying to understand it. I like the idea that a black hole is a dark star and the sun is the bright star, because they are related. When a star collapses, it creates a black hole, and so it's very interesting. It's a very interesting relationship. And so I think this just helps illustrate that. I don't know if he's actually talking about facts, but yeah. But that was cool. I don't remember this. He might not have shown up. I don't know. Damn, I didn't know. Like, people are just advertising on this shit. That's cool. I might try. I don't know. But I think that almost covers everything. And then... Oops, come on. Why is this everything freezing? Hello. Okay. Let's see. Then... I went to the grad school fair. I talked to a few people about applying for a PhD. Shobita encouraged me to apply for a PhD at North Carolina Agricultural and Technology. She is, like I said, she was just the sweetest person. Yeah. And so that's the grad school, and then we had the banquet. A couple people won awards. Like Caden won an award. This was cool. Jay Matthews, he was a cool guy, talking about optics and the things that light can help work with, like detecting gravitational waves, how it helped create the internet. It was really nice. It was cool. It's good talk. Breakfast was, just fruit and stuff. Department tours, we got to go around, check out everything. It just keeps freezing. Okay, we're back. Department tours. Yeah, we just checked everything out, the equipment and stuff. They use like atomic molecular optics to map out biology. So I was super interested in that. And grad school panel discussion, they just talked about like applying. That was a great little thing. Got to talk with the grad students there. They were nice. They gave me some good barbecue recommendations. I didn't get to go to it. I went to the other recommendation just because it was closer and I think it was a little bit cheaper. Next time I'm going there for sure. Midtown Wood something. I got it written down. I got it. I know where it is on the map-ish too. I know it's by Midtown. So it's like the north. It's just like north of Charlotte. I can't remember if it was a little bit west or a little bit east, but it's north. I think it was a little bit west. But yeah, and then the closing planetary session, gravitational waves. That was cool. This I feel bad. I was like falling asleep in this. But it was good. Scott's a good speaker. Just when there's so much math, because he's talking about the stochastic background and frequencies and stuff, and when it doesn't matter what class it is when we start getting into the math, I start falling asleep. But it also helps me like understand the math better later on. I can't explain it. It's just how I've done it before, and I became good at math, so maybe it's not causal. This was cool. He talked about general relativity, and one person asked, like, so what are the flaws of general relativity? And it doesn't, in order for like quantum mechanics and general relativity to agree with each other, then it would have like an infinite number of constants and variables moving, and it would just be too much mathematics. And so there's nothing that connects general relativity and quantum mechanics as of right now, but both seem to be correct. So that's kind of what I gathered from it. And yeah, that's the whole conversation. You know what, we're gonna just do it here. Boom. Okay, let me fix this. Okay, so this is going to be the water bending experiment. Okay, cool. So in this study, he proposed 3 models: a large dipole moment of the water molecule, ions dissolved in the water, and triboelectric charging. And the triboelectric charging was specific to the faucet, influencing the water or the liquid. And that's important because as we go into this, you're going to see a different kind of results. So, blow up the balloon, charge it up. So you could see it move right there on the hot water. And yeah, so that pull effect is what we're looking at. And then cold water. I'm going to have to slide this over a little more. And bottle test. So this is where I put all the different liquids into to test it. And you'll get to see a much more strong pull. So it goes straight down, and then you can see it just jumping towards the balloon as the balloon gets closer. Then the water gets closer to the balloon. And so distilled water has no minerals in it, or very like minimized, and then spring water has minerals in it. And so you can't really tell if the charging on the balloon is equal for each experiment. All you can really know is if there's a positive charge or not. And so just having a positive result from the spring water is enough. And so it's hard to judge really which liquids move more or less. I guess that's not entirely true, because you'll see at the very end, alcohol is crazy. And so this one is the white vinegar, also moves. Kind of look like the distilled water moved the most so far. And so could suggest a large dipole moment, but this is the thing, because before this, Dr. Anders told me that it was the triboelectric effect. I finally got it out of him. I kind of figured that from the way he was talking, but I was not able to get oil to get pulled by the triboelectric effect of the balloon, because the balloon has that charge. That triboelectric effect is essentially static electricity. So the balloon's getting charged by it, but the oil is not getting charged by the bottle. And the argument is that they have to be in agreement for the triboelectric effect to be of enough effect to come from the bottle. And so this is avocado oil, because I ran out of vegetable oil. And this is just, I only had a little bit of avocado oil, but I put it all in the bottle just to try. I think then I just dumped it out. Like, I wasted a lot, but I kind of want to make sure I had enough volume to maintain a reasonable flow. I'm just trying to make sure that the balloon still has some kind of effect, and it wasn't just that it stopped charging for some reason, and so, or the bottle wasn't giving off the effect like it was before. That I just had to make sure something was happening on this equipment stuff. And as everything still gets pulled. Oh, is that still water? Yeah. And then this is olive oil. As you can see, like, the water will move, but the oil will not. And the water will move and the oil will not. And if you really look down low, wow, right there, you can see the water tail of it moving and shifting towards the balloon. But the oil does not at all. And then I tried mineral oil, because when I was at the store, I just saw mineral oil. I was like, oh, minerals and oil, of course, for like a skincare routine or something. And it's a laxative that they get from petroleum. So they're just hydrocarbons, and it's non-polar, just like another oil. This is 3% hydrogen peroxide. It's kind of hard to see, but it has a strong response. It moves fairly far. And then alcohol. There's no more volume on this one, but this one had, I think, the greatest movement. It's 9% water, 91% alcohol. And so because the alcohol is very unstable, it likes to dissolve in the air very quickly. And so as it's dissolving and releasing, and becoming into a gas, it might have much less inertial properties than it does in the liquid, and so it could be much more receptive to the triboelectric effect of the balloon. That's my best guess. But yeah, that's it, and that kind of covers everything. I also wanted to shout out Adrian Gutierrez. Hell yeah, he's the man. Experimental nuclear and particle physicist. And he was convinced, I was able to convince him of my theory as well. So here is what he was studying and presenting at the Physics Society. He was very encouraging about presenting new data and following the evidence above following tradition. And so this was really cool. So shout out to Adrian Gutierrez. He is brilliant, obviously. But yeah, I just want to make sure I shout him out. Thanks, man. Thank you for your support, and thank you for your company. It was great talking with you. All right, so that was SESAPS, SESAPS, Southeastern Section, and so I got people convinced. I got nuclear and particle physicists convinced. I don't know if I count him as a particle physicist, because that's what he's studying, and he works at CERN, and he's at least a particle physicist technician with all the work he's done. So I was able to convince a particle physicist technician. Oh, I I gotta go back. Didn't ask her at the time. Cannot figure it out. But I'll say biophysicist. She's very nice. She's very sweet. I don't know how much publicity she wants, but luckily this isn't getting a lot of publicity. So, yeah, at least a nuclear physicist, at least a particle physicist technician. Hard to say where Igor landed on it as a quantum physicist, but I would say interested, at least. He was very kind. And the biophysicist Shobita, a biochemist. I think I got Kenzie kind of convinced, but I think other people convinced her. Who cares? And I guess you can make the argument that that's what a nerd would say, but it's like, because it's the battle of the jocks and the nerds right now, and I am trying to bring around the revenge of the nerds. I'm trying to help y'all get really strong and have better techniques and engineering systems for yourself. And I don't understand why you don't believe it's possible, because you can engineer everything else in the universe, but you don't think you can engineer your own body. You say it's infinitely complex, and it's not. It's finitely complex. Finitely complex. And that's the important thing. I'll be done with this video. Thanks. And yeah, talk to y'all later.